In the 1970s, something was wrong with the universe, or at least our understanding of it. Vera Rubin and her colleague Kent Ford were looking at the Andromeda Galaxy. They were measuring how fast its stars were moving. They expected to see stars at the edge of the galaxy moving slower than the stars near the center. That's how gravity works. The planets in our solar system do this. Mercury zips around the sun. Neptune crawls. It's simple physics. But that's not what they saw. The stars on the very edge of Andromeda were moving just as fast as the stars closer in. It made no sense. It was like watching the outer horse on a merry-go-round keep pace with the inner horse. For that to happen, there had to be a huge amount of invisible mass, a huge source of gravity, extending far beyond the visible stars. They looked at other galaxies. They saw the same thing over and over. The math was undeniable. The visible stuff, the stars and gas and dust we could see, only accounted for about 15% of the gravity needed to hold these galaxies together. The other 85% was missing. It was there, its gravity was real, but it was completely dark. They called it dark matter. The work of Rubin and Ford was a quiet revolution. It proved that everything we had ever seen, every star, every galaxy, every planet, was just a tiny fraction of what the universe is actually made of. We are profoundly ignorant. We live in a cosmos dominated by an invisible substance we don't understand. This is the background for the James Webb Space Telescope. It's a machine built to stare into the darkness and find answers to questions born from discoveries like Rubin's. It's not just about pretty pictures. It's about confronting our cosmic ignorance one mystery at a time. Number 20. The first light was not from stars. The universe was completely dark for about 370,000 years after the Big Bang. It was a hot, dense fog of hydrogen and helium plasma. The light couldn't travel. Electrons were not bound to atomic nuclei. Then, as the universe expanded and cooled, electrons and nuclei combined to form neutral atoms. This event is called recombination. For the first time, light could travel freely across space. This first light is what we now see as the cosmic microwave background, or CMB. It was released everywhere at once. The temperature of the universe at that time was about 3,000 Kelvin. Today, due to the expansion of space stretching the light waves, we detect this light as microwaves at a temperature of just 2.7 Kelvin. So the very first light was a uniform faint glow filling the entire universe, not the pinprick of a star. The age that followed, from about 370,000 years to maybe a few 100 million years after the Big Bang, is called the Cosmic Dark Ages. There were no stars, there were no galaxies, it was just a vast, dark expanse of neutral hydrogen and helium gas slowly clumping together under the influence of dark matter. Webb cannot see the cosmic microwave background. That's a job for different telescopes. But its mission starts right at the end of the Dark Ages. Its primary goal is to find the very first stars and galaxies that lit up the universe and brought this darkness to an end. These first stars were not like our sun. Theory says they were monsters, hundreds of times more massive. They were made of only hydrogen and helium, the pristine elements from the Big Bang. Because of their immense mass, they burned incredibly hot and incredibly fast. They lived for only a few million years before exploding as supernovae. Our sun, by contrast, will live for about 10 billion years. These first stellar explosions were critical. They forged the first heavy elements like carbon, oxygen, and iron, and blasted them out into space. These elements were the seeds for the next generation of stars, for planets, and eventually for us. Finding these first stars, called population the third stars, is one of the hardest things in astronomy. They are unbelievably far away. The light from them has been traveling for over 13.5 billion years. The expansion of the universe has stretched their bright, blue, and ultraviolet light so much that by the time it reaches us, it's in the infrared part of the spectrum. And human eyes can't see it. The Hubble Space Telescope can't see it well either. It's mostly an optical telescope. This is exactly what Webb was built for. It is a giant infrared eye. It can stare at a patch of sky for a long time, collecting these faint, ancient photons. It's looking for the moment the cosmic dawn broke. It is trying to find the first pinpricks of light that ended the darkness. It's not just about finding a dot. By using its spectrographs, Webb can analyze the light from the most distant objects it finds. If it finds a galaxy with stars that have absolutely no heavy elements, it will know it has found a piece of the primordial universe. It will have seen the children of the Big Bang. Early results have been stunning. The Webb has already found galaxies that existed just 300 million years after the Big Bang. These are far earlier and more numerous than models predicted. This suggests the cosmic dark ages may have ended sooner than we thought. The universe might have woken up faster, but the true first light from the first single star remains elusive. It might be that they are too faint even for Webb, or they formed in small clusters that Webb sees as a single blob. The search continues. It's a search for our ultimate cosmic origins. Number 19, supermassive black holes should not exist so early. At the center of almost every large galaxy, including our own Milky Way, there is a supermassive black hole. Our galaxy's black hole, Sagittarius A, is about 4 million times the mass of our sun. The one in the Andromeda galaxy is about 100 million solar masses. The one in the galaxy M87, the first one we ever took a picture of, is 6.5 billion solar masses. These are giants. A big question is, how did they get so big? The standard idea is that they grew over time. A smaller black hole, maybe from a collapsed massive star, would sit at the center of a young galaxy. Over billions of years, it would swallow gas, dust, and stars. It would also merge with other black holes when galaxies collided. It's a slow, steady process of accumulation. This story works well for the black holes we see in the nearby universe. But here's the problem. Astronomers have found supermassive black holes, 1 billion times the mass of the sun, in the very early universe. We have seen quasars, which are incredibly bright galactic centers powered by these black holes that existed less than 700 million years after the Big Bang. The universe is about 13.8 billion years old. This is like seeing a fully grown adult who is only 3 years old. There just wasn't enough time for a normal stellar mass black hole to grow that big through the standard process. You would have to be feeding it material at an impossible rate, far beyond what physicists think is stable. So how did they get there? This is a major mystery. There are a few ideas. One is called direct collapse. In this scenario, a truly enormous cloud of primordial gas in the early universe, perhaps hundreds of thousands of solar masses, could have collapsed directly into a massive black hole, skipping the star phase entirely. This would give it a huge head start. These would be black hole seeds that were already massive from birth. Another idea involves the very first stars, the population the third stars. Since they were so massive when they died, they might have left behind black holes that were also larger than usual, maybe 100 solar masses. If these early stars formed in dense clusters, these black holes could have quickly merged and grown into an intermediate mass black hole, which then acted as the seed. The problem with testing these theories is that they happened in the earliest moments of the universe. The light from these events is extremely faint and redshifted into the infrared. Hubble couldn't see the small, faint host galaxies around these first quasars. It could see the bright quasar itself, but the galaxy it lived in was just a blur. This is where Webb changes everything. With its infrared vision and incredible sensitivity, Webb can peer into the cosmic dawn and see the environments where these first monster black holes formed. It can see the host galaxies. It can measure how fast stars are moving around these black holes to accurately weigh them. It can see if they are in the process of merging with other galaxies. Webb is looking for the seeds. Are there lots of smaller black holes in early galaxies? or does it see evidence of direct collapse black holes? By taking a census of black holes in the first billion years of the universe, Webb will provide the crucial data to figure out which theory, if any, is correct. It might be that the physics of black hole growth needs to be rewritten. Maybe they can feed much faster than we thought. Or maybe something entirely new and unexpected was happening in the chaotic, dense environment of the early cosmos. Webb is our time machine to watch it happen. Number 18, the universe is mostly made of something we cannot see. For every star, planet, and cloud of gas you can see, there is more than 5 times as much dark matter that you cannot. This invisible substance makes up about 27% of the universe. The normal matter we are made of is less than 5%. The rest is dark energy. We know dark matter is real because we see its gravity at work. Vera Rubin's work on galaxy rotation was the key evidence. Galaxies are spinning so fast they should fly apart, but the extra gravity from a halo of dark matter holds them together. We also see it through gravitational lensing. A massive object, like a cluster of galaxies, warps space-time. Light from a more distant galaxy passing by this cluster will be bent, like light through a lens. This creates distorted, magnified, or multiple images of the background galaxy. We can measure how much the light is bent and calculate the mass of the lensing cluster. The result is always the same. There is far more mass than we can account for with the visible galaxies alone. The extra mass is dark matter. The bullet cluster is one of the most famous examples. It's actually 2 galaxy clusters that have passed through each other. The hot gas from the clusters, which is normal matter, collided and slowed down in the middle. But the dark matter, which doesn't interact with normal matter except through gravity, seems to have passed right through without slowing down. The lensing shows that most of the gravity, most of the mass, is located where the dark matter is, not where the visible glowing gas is. But what is it? We have no idea. It's not just dark clouds of normal matter, because we would be able to detect them in other ways. It has to be some new kind of particle, something not included in the standard model of particle physics. The leading candidate for a long time was a WIMP, or weakly interacting massive particle. These are hypothetical particles that would be heavy and would only interact through gravity and the weak nuclear force, making them nearly impossible to detect. Huge experiments have been built deep underground to try and catch a WIMP bouncing off a nucleus, but so far they have found nothing. Another candidate is the axion, a much lighter hypothetical particle. So how can a telescope help find a particle it can't see? Or a Webb can't detect a dark matter particle directly, but it can map its effects with incredible precision. The primary theory is called cold dark matter. Cold just means the particles were moving slowly in the early universe. This theory predicts that dark matter first clumped together into small halos. Then, these small halos merged over time to form bigger and bigger halos, and normal matter was pulled in by their gravity to form the galaxies we see today. You know, it's a bottom-up process. You know, small things form first. Webb is the ultimate test for this theory. By looking back to the very first galaxies, it is seeing how cosmic structure began. It is mapping the distribution of the earliest, smallest galaxies. If cold dark matter is correct, there should be a certain number of small, faint galaxies forming in their little dark matter halos. If Webb sees something different, for example, if the first galaxies are much larger or smoother than predicted, it might mean dark matter is warm or fuzzy, with particles that moved faster and washed out the smallest structures. Webb's deep field images are essentially maps of the dark matter scaffold of the early universe. By studying how the very first galaxies are clustered together and how their light is lensed by foreground dark matter, Webb is providing the most detailed picture yet of this invisible cosmic web. This data will constrain the properties of the dark matter particle even if we can't hold it in our hands. It can tell us if it's cold, warm, or something else entirely, narrowing down the search for the particle physicists on the ground. Number 17, the universe's expansion is a source of cosmic conflict. We know the universe is expanding. In the 1920s, Edwin Hubble observed that distant galaxies are all moving away from us. And the farther away a galaxy is, the faster it's moving away. This is described by the Hubble constant, a number that tells us the rate of expansion. The problem is, we have two main ways of measuring this number, and they give different answers. This disagreement is called the Hubble Tension, and it's one of the biggest problems in cosmology today. One way to measure the Hubble constant is by looking at the local universe, the one relatively close to us. This method uses a cosmic distance ladder. You start by measuring the distance to nearby stars using parallax, which is a simple geometric trick. Then you find special types of stars called Cepheid variables in those same nearby galaxies. Cepheids have a very useful property. Their brightness pulsates at a rate directly related to their true luminosity. So if you measure how fast one pulsates, you know how bright it really is. By comparing its true brightness to how dim it appears from Earth, you can calculate its distance. Once you have the distances to galaxies with Cepheids, you can look for a much brighter standard candle in those same galaxies, type Ia supernovae. These are exploding white dwarf stars that all reach the same peak brightness. They are so bright they can be seen across the universe. So you calibrate the brightness of these supernovae using the Cepheid distances. Then you find these supernovae in very distant galaxies and use them to calculate the expansion rate. This local measurement, refined over many years and most recently using the Hubble Space Telescope, gives a value of about 73 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. This means for every megaparsec farther away a galaxy is, it appears to be receding from us 73 kilometers per second faster. The second method looks at the very early universe. It uses the light from the cosmic microwave background CMB, the afterglow of the Big Bang. The Planck satellite has mapped the CMB in incredible detail. In this ancient light, there are tiny temperature fluctuations. These were the seeds of all future structure. By studying the size of these fluctuations and using our best model of cosmology, the lambda CDM model, which includes dark matter and dark energy, we can predict what the expansion rate should be today. This method gives a value of about 67 kilometers per second per megaparsec. The two numbers, 73 and 67, disagree, and their error bars do not overlap. This isn't a small measurement error, it's a fundamental conflict between the physics of the early universe and the universe we see today. Something is wrong. Either there is a hidden error in one of the measurement techniques, or our model of the universe is incomplete. This is where Webb comes in. Webb's job is to refine the local measurement with unprecedented accuracy. The Hubble Space Telescope, which made the previous best measurements, has a limitation. When looking at distant Cepheids and supernovae, its vision can be blurred by dust and by the light of other stars crowded around them. Webb is an infrared telescope. Infrared light cuts through dust much better than visible light. This gives Webb a much clearer view. It can more cleanly isolate the Cepheid variable stars from their neighbors, reducing a major source of uncertainty. Webb is currently re-observing the Cepheids that Hubble used, and also looking at new ones farther out, to rebuild the cosmic distance ladder from the ground up with higher precision. If Webb's measurement confirms the 73 value and shrinks the error bars, it will mean the Hubble tension is undeniably real. It would be strong evidence that there is new physics waiting to be discovered. Perhaps dark energy isn't a constant, but has changed over time. Perhaps there's a new type of particle, sometimes called dark radiation, that was present in the early universe. Or maybe our understanding of gravity is wrong. By sharpening this conflict, Webb is pushing cosmology to a breaking point. And that's often where new discoveries are made. Number 16, the building blocks of life are floating in space. Carbon, hydrogen, oxygen, nitrogen. These are the main elements of life as we know it. We are, as Carl Sagan said, made of star stuff. The first generation of stars cooked up these heavy elements and spewed them into space. The next generations of stars and planets formed from this enriched material. But going from simple elements to complex molecules is a big step. Where did the building blocks of life, things like amino acids and complex organic molecules, come from? Were they forged on a young Earth, or did they form in space and get delivered here by comets and asteroids? Increasingly, evidence points to space. We've found organic molecules in meteorites that have landed on Earth. We've seen the chemical signatures of them in the cold, dark molecular clouds where new stars are born. These clouds are vast, cold, and dark. They are stellar nurseries. Inside them, on the surfaces of tiny dust grains, a rich chemistry takes place. Simple molecules like water, carbon monoxide, and ammonia freeze onto these grains, forming icy mantles. Over millions of years, faint starlight provides the energy to break these simple molecules apart and allow them to recombine into much more complex and interesting things. This includes things like alcohols, sugars, and the precursors to the molecules of life. The problem is that these molecular clouds are, by definition, very dark and dusty. Visible light cannot penetrate them. We can study them with radio telescopes, which can detect the specific frequencies emitted by different molecules as they rotate. But this only gives us part of the picture. We want to see what's frozen in the ice. This is a perfect job for Webb. Its infrared vision can pierce through the dust. More importantly, it has powerful spectrographs that can perform absorption spectroscopy. This is how it works. Webb looks at a bright star that is located behind a dark cloud. The starlight travels through the cloud on its way to the telescope. As it passes through, the molecules in the cloud's ice and gas will absorb very specific frequencies of infrared light. Each molecule has a unique absorption fingerprint. So, by looking at the starlight spectrum and seeing which infrared colors are missing, scientists can determine exactly what molecules are present in the cloud, what state they're in, ice or gas, and how abundant they are. It's like a cosmic barcode scanner. Webb is using this technique to take a chemical inventory of stellar nurseries. One of its early targets was the chameleon Y molecular cloud. It found evidence for a whole range of complex organic molecules frozen in the ice, including methanol and likely ethanol and others. It showed that the building blocks for planets and perhaps life are present even before the star has fully formed. It's also looking at protoplanetary disks, the swirling disks of gas and dust around young stars where planets are forming. Where it wants to trace the journey of these molecules from the parent cloud into the disk and see how they are distributed. Are the ingredients for life more common in the habitable zone of a disk where a planet like Earth might form? By understanding the chemistry of these planet-forming regions, we can understand what raw materials were available for a young Earth. Did our planet have to start its chemical journey from scratch, or was it born from a disk already seeded with the complex molecules needed for life? Webb's observations suggest the latter. The ingredients weren't just available, they were common. This implies that the potential for life might be widespread throughout the galaxy. Number 15, we are watching planets being born. For a long time, planet formation was just a theory. The idea was that after a star forms, it's surrounded by a rotating disk of leftover gas and dust. This is called a protoplanetary disk. Within this disk, tiny dust grains start to stick together, a bit like dust bunnies under your bed. They form pebbles, then rocks, then boulder-sized planetesimals. These planetesimals collide and merge, and their gravity grows, allowing them to attract more material. Eventually, after millions of years, they grow into planets. The gas giants, like Jupiter, would have formed far from the star where it was cold enough for ices to condense, giving them more solid material to build a core and then rapidly accrete huge amounts of gas. The rocky planets, like Earth, would have formed closer in where it was too hot for ices. It's a neat story, but seeing it happen is hard. Protoplanetary disks are relatively small and often shrouded in the dust of their parent nebula. Well, Hubble could take pictures of some of the brighter, larger disks, like the one around the star Fomalhaut. The Atacama Large Millimeter Submillimeter Array ALMA, a radio telescope in Chile, has been revolutionary. It can peer into the cold, dark midplanes of these disks and has taken incredible images showing rings and gaps, which are thought to be the telltale signs of planets clearing out their orbits as they form. But ALMA primarily sees the larger dust grains. It doesn't tell us much about the gas or the inner regions of the disk where rocky planets form. This is the gap Webb is designed to fill. Webb's infrared instruments are perfectly suited to study the warm dust and gas in the inner parts of these disks. It can see the material that is actively building planets like ours. One of its key tools is spectroscopy. By analyzing the light coming from different parts of a disk, Webb can create a chemical map. It can see where water ice is, where carbon monoxide is, and where complex organic molecules are located. This is crucial. It tells us what materials are available to forming planets at different distances from their star. For example, the location of the Snell line, the point in the disk where water freezes into ice, is thought to be a key factor in planet formation. Webb can pinpoint this line. It's not just about static pictures. Webb can also watch the disks evolve. It can look for asymmetries or clumps in the disk that might be the beginnings of a planet. It can study the winds and accretion flows that carry material from the disk onto the young star. It is observing a whole range of disks, from very young ones that are just beginning to form planets to older ones where the process is nearly complete. By comparing them, scientists can piece together a timeline of planet formation. An early, exciting discovery came from observing the disk around a very low-mass star. Webb's MIRI instrument detected a rich assortment of carbon-bearing molecules like acetylene and benzene in the inner part of the disk, where rocky planets would form. This was a surprise. Scientists thought the harsh radiation from the star would destroy these molecules so close in. Their presence suggests that the raw materials for carbon-rich planets might be more common and resilient than previously believed. Webb is moving us from a cartoon sketch of planet formation to a detailed, high-resolution movie. It's providing the ground truth to test our computer models. It's watching the chaotic, dusty process that 4.5 billion years ago led to the creation of our own world. Number 14, most planets in our galaxy are nothing like ours. For centuries, our solar system was the only one we knew. We had small, rocky inner planets and big, gassy outer planets. We assumed this was the standard model. Then, in 1995, astronomers discovered the first exoplanet orbiting a sun-like star, 51 Pegasi b. It was a complete shock. It was a gas giant, about half the mass of Jupiter, but it was orbiting its star in just 4 days. It was incredibly close, far closer than Mercury is to our sun. It was a hot Jupiter. This discovery shattered our assumptions. Since then, we've found thousands of exoplanets, and the diversity is staggering. There are hot Jupiters, there are super-Earths, planets bigger than Earth but smaller than Neptune, a type of planet we don't even have in our solar system. There are mini Neptunes, which seem to be the most common type of planet in the galaxy. There are planets orbiting 2 stars, planets in highly eccentric orbits, and planets that have been ejected from their systems and now wander through space as rogue planets. The universe is more creative at building solar systems than we ever imagined. The Kepler Space Telescope was a planet hunting machine. It stared at one patch of sky for years, waiting for the tiny dip in a star's light caused by a planet passing in front of it, an event called a transit. Kepler found thousands of planets and gave us our first real statistics on planet populations. But Kepler had its limits. It told us a planet's size and its orbit, but not much else. To really understand a planet, we need to know its mass and what its atmosphere is made of. Getting a planet's mass requires other techniques, like measuring the wobble of its host star, but studying its atmosphere is the key to understanding its climate, its composition, and whether it could potentially support life. This is one of Webb's primary missions. When a planet transits its star, a tiny fraction of the starlight passes through the upper layers of the planet's atmosphere. Different molecules in the atmosphere absorb specific wavelengths of light. Webb's spectrographs can analyze the starlight before, during, and after the transit. By seeing what light is missing during the transit, scientists can figure out what the atmosphere is made of. This is called transmission spectroscopy. It's an incredibly difficult measurement. The atmospheric signal is tiny, just a few parts per million of the total starlight. But Webb's large mirror and sensitive instruments are up to the task. It has already made groundbreaking discoveries. It made the first confirmed detection of carbon dioxide in the atmosphere of an exoplanet, WASP-39b, a hot gas giant. It has also found evidence of sulfur dioxide, which suggests active photochemistry, a process where starlight breaks down molecules. It even detected patchy silicate clouds, essentially clouds of fine sand. For another planet, K2-18b, a super-Earth in the habitable zone of its star, Webb found carbon-bearing molecules like methane and carbon dioxide. Intriguingly, it also saw a possible hint of a molecule called dimethyl sulfide. On Earth, this molecule is only produced by life, mostly marine phytoplankton. This is not a detection of life, and the signal is tentative. But it shows the power of Webb to search for these biosignatures, molecules that could hint at biological processes. Webb is now starting a systematic survey of dozens of exoplanet atmospheres, from hot Jupiters to potentially habitable super-Earths. It is creating the first catalog of atmospheric compositions, allowing us to compare different worlds. Is water common? Are clouds common? Do rocky planets around small red dwarf stars have atmospheres at all? By answering these questions, Webb is transforming exoplanet science from just stamp collecting to true comparative planetology. It's revealing the vast and strange planetary zoo out there. Number 13, there is a system of 7 Earth-sized worlds next door. Just 40 light years away, there is a star system that seems like something out of science fiction. It's called TRAPPIST-1. The star itself is tiny. It's an ultra-cool red dwarf, not much larger than the planet Jupiter and far less massive than our sun. And orbiting this dim little star are at least 7 rocky planets, all roughly the size of Earth. What's more, at least 3 of these planets orbit within the star's habitable zone, the region where temperatures could be just right for liquid water to exist on their surfaces. This is an incredible discovery. It's the largest number of terrestrial planets ever found around a single star, and it's in our cosmic backyard because the star is so small and dim, the planets orbit very close to it. The entire TRAPPIST-1 system would fit comfortably inside the orbit of Mercury. The innermost planet completes an orbit in just 1.5 Earth days. The outermost one takes about 18 days. They are so close to each other that if you were standing on the surface of one, the other planets would appear in the sky as large as our moon, or even larger. This system is a perfect natural laboratory for studying the formation and evolution of rocky planets. And because the star is so small, it makes studying the planet's atmospheres much easier. When a planet transits a small star, it blocks out a larger percentage of the star's light, making the signal easier to detect. Also, the atmospheric signal during a transit is stronger relative to the starlight. This makes the TRAPPIST-1 system one of the highest priority targets for the James Webb Space Telescope. Webb is systematically studying these 7 worlds. The key questions are, do they have atmospheres? And if so, what are they made of? These are not trivial questions. Red dwarf stars are notoriously tempestuous, especially when they are young. They can unleash powerful flares of radiation that could strip away the atmospheres of any closely orbiting planets. It's possible that the TRAPPIST-1 planets are bare, airless rocks, or they could have thick, crushing atmospheres like Venus, or thin ones like Mars. Or just maybe, one could be like Earth. Webb is using its transit spectroscopy technique on each of the planets. The first results have started to come in. For the innermost planet, TRAPPIST-1b, Webb's observations suggest it has no significant atmosphere. The data is a flat line, meaning no starlight was absorbed. This isn't entirely surprising, given how close it is to the star and the intense radiation it receives. It is likely a hot, barren rock. For another planet, TRAPPIST-1c, the results are similar. It also appears to be an airless world. But the investigation is just beginning. Webb is scheduled to observe all the planets, including those in the habitable zone D, E, and F. The presence of an atmosphere, especially one containing water, carbon dioxide, or methane, would be a monumental discovery. It wouldn't mean life, but it would mean the planet is a much more interesting place to look. Webb can also measure the planet's temperatures directly. As a planet orbits its star, we see different phases, just like we see with our moon. When the planet is on the far side of the star, we are seeing its day side. By measuring the infrared light from the system, Webb can distinguish the light from the star alone versus the star plus the planet's thermal emission. This tells us how hot the planet is. For TRAPPIST-1b, the dayside temperature was measured to be around 500 Kelvin, about 230 Celsius. Which again supports the idea of it being a dark, airless rock with no atmosphere to redistribute heat. The TRAPPIST-1 system is a test case. Can habitable worlds exist around the most common type of star in the galaxy? Red dwarfs make up about 75% of the stellar population. If the answer is yes, then the number of potentially habitable planets in the Milky Way could be enormous. If the answer is no, it might mean that stars like our Sun are the best places to look. The Webb is giving us our first real answers. For number 12, our solar system has hidden oceans. For a long time, we thought Earth was the only ocean world in our solar system. And we looked for life on Mars, a dry, dusty planet. But over the last few decades, our perspective has shifted outwards. We've discovered that some of the most promising places to look for life are not on planets, but on the moons of the gas giants Jupiter and Saturn. And the key ingredient is water. Jupiter's moon, Europa, is a prime example. On the surface, it's a ball of ice, cracked and streaked with reddish-brown material. Its surface temperature is a frigid 160 Celsius. But data from the Galileo spacecraft showed strong evidence that beneath this ice shell, which might be several kilometers thick, there is a vast global ocean of liquid salt water. There is likely more liquid water on Europa than in all of Earth's oceans combined. This ocean is kept liquid by tidal heating. As Europa orbits Jupiter, the massive planet's gravity constantly tugs and flexes the moon's interior, generating heat. This same process is what powers volcanoes on Jupiter's other moon, Io. On Europa, it melts the ice from below. So you have the three key ingredients for life, as we know it: liquid water, a source of energy, tidal heating, and the necessary chemical elements which would be leached from the rocky seafloor. Similarly, Saturn's tiny moon Enceladus was a huge surprise. The Cassini spacecraft flew through giant plumes of water vapor and ice particles erupting from cracks known as tiger stripes near the moon's south pole. It essentially flew through a geyser from an alien ocean. Analysis of the plume's composition showed it contained not just water, but also salts, silica dust, indicating hydrothermal activity on the seafloor, like the black smokers on Earth's ocean floors, and complex organic molecules. Enceladus has a subsurface liquid water ocean, and it is actively venting it into space. This is a tantalizing discovery. It means we could potentially sample an alien ocean without ever having to land and drill through miles of ice. The James Webb Space Telescope is not a primary mission for studying solar system bodies. Its main job is to look at the distant universe, but its capabilities are so powerful that it can make unique contributions right here at home. Webb is observing both Europa and Enceladus. For Enceladus, Webb's incredibly sensitive spectrographs are being used to analyze the composition of its plumes with far greater detail than Cassini could. Cassini's instruments were amazing, but they were designed in the 1990s. Webb is state-of-the-art. It's searching for more complex organic molecules and looking for specific chemical markers that could hint at biological processes. A key goal is to understand the source of the plumes and how they connect to the ocean below. Webb recently made a stunning discovery at Enceladus. It observed a water vapor plume stretching more than 9,600 kilometers into space, nearly the distance from Los Angeles to Buenos Aires. This is far larger than previously seen and shows just how active this little moon is. For Europa, the situation is a bit different. We have seen hints of water plumes with the Hubble Space Telescope, but they are much more sporadic and harder to confirm than the ones on Enceladus. Webb is staring at Europa, hoping to catch a plume in the act. If it does, it can perform the same kind of detailed chemical analysis. But even without a plume, Webb can study Europa's surface composition in unprecedented detail. It can map the distribution of salts and organic materials on the surface, which could give clues about the composition of the ocean below and how material from it might be reaching the surface. Webb's observations are complementary to upcoming missions like NASA's Europa Clipper, which will fly by Europa many times, and the European Space Agency's JUICE mission. While those probes will get up close and personal, Webb provides the wider context and powerful chemical analysis from a distance. It's helping us understand these hidden oceans and prioritize where to look for life beyond Earth. Number 11, the Kuiper Belt is a graveyard of the solar system's birth. Beyond the orbit of Neptune, from about 30 to 50 times the Earth-Sun distance, lies a vast icy realm called the Kuiper Belt. It's a bit like the asteroid belt, but far larger and more massive. It is populated by hundreds of thousands of icy bodies larger than 100 kilometers across, and an estimated trillion or more comets. Pluto is the most famous resident of the Kuiper Belt. These objects are not just inert ice balls, they are time capsules. They are the leftover building blocks, the planetesimals from the formation of our solar system 4.6 billion years ago. While the material in the inner solar system was baked by the sun and churned up to form the rocky planets, the objects in the Kuiper Belt have remained in a deep freeze, largely unchanged since their birth. Studying them is like performing archaeology on our own origins. They hold clues about the chemical composition and physical conditions of the early solar nebula. But studying them is incredibly difficult. They are small, extremely far away, and very faint. They reflect very little sunlight. From Earth, even the largest Kuiper Belt objects, KBOs, are just tiny points of light in our best telescopes. We've sent one spacecraft there, New Horizons, which gave us stunning close-up views of Pluto, and another KBO, Arrokoth. But that was just a flyby of two objects out of millions. To understand the whole population, we need telescopes. This is where Webb's sensitivity is a game changer. Webb can study KBOs that are too faint for any other telescope to see. One of its key programs is a survey of these objects. It's not just about counting them. Webb uses its spectrographs to analyze the weak, reflected sunlight from their surfaces. This tells us what their surfaces are made of. We know they are rich in water ice, but Webb can detect other, more exotic ices like methane, nitrogen, carbon monoxide, and ammonia. It can also identify complex organic molecules, the reddish-brown tholins that are thought to be created when simple organic ices are irradiated by sunlight and cosmic rays. By studying the chemical makeup of a large sample of KBOs, scientists can look for patterns. Do objects that formed closer to the sun have a different composition from those that formed farther out? This can help us reconstruct the chemical map of the early solar system. Webb is also looking at an unusual property of many KBOs. They come in pairs. Many of them are binary systems with two objects orbiting each other. Pluto and its large moon Charon are a prime example. Understanding how these binaries formed tells us about the conditions in the early Kuiper Belt. Were they formed from gentle collisions in a much more crowded environment? Webb can study the colors and compositions of both members of a binary pair to see if they formed together from the same material. Furthermore, Webb is studying some of the strangest KBOs. Take Haumea, a large oval-shaped object that spins incredibly fast, completing a day in just 4 hours. It's also surrounded by a ring of particles and has 2 small moons. Webb is studying the composition of Haumea and its family to try and understand the giant collision that likely gave it these bizarre properties. Another target is Sedna, an object with a truly enormous elliptical orbit that takes it more than 900 times farther from the sun than Earth. Its origin is a complete mystery. By studying the composition of these outliers, we can get clues about the chaotic early history of our solar system, a time when the giant planets may have migrated and scattered these smaller bodies into their strange orbits. Webb is opening up this dark, distant region of our own solar system in a way that was never possible before. Number 10, stars are born in secret. The birth of a star is one of the most fundamental processes in the cosmos. It happens inside giant, cold clouds of gas and dust called molecular clouds. Within these clouds, dense clumps can collapse under their own gravity. As a clump collapses, it spins faster and heats up, forming a protostar at its center. This protostar is surrounded by a swirling disk of material that feeds it, helping it grow. For millions of years, the protostar continues to accrete mass until its core becomes hot and dense enough for nuclear fusion to begin. At that moment, a star is born. The whole process is hidden from view. The very dust and gas that form the star also act as a thick shroud, blocking visible light. If you look at a picture of a stellar nursery like the Pillars of Creation in the Eagle Nebula with the Hubble Telescope, you see majestic towers of gas and dust. But you can't see what's happening inside them. We have been able to study star formation using radio and submillimeter telescopes, which can detect the cold dust and gas, but they don't have the sharpness to see the fine details of the protostar and its disk. We have been missing a crucial part of the story. The James Webb Space Telescope is changing that. Its powerful infrared vision can cut through the obscuring dust and reveal the newborn stars within. It's like having an X-ray machine for the universe. Webb's images of the Pillars of Creation are a perfect example. Where Hubble saw opaque clouds, Webb sees through them, revealing hundreds of newly formed stars glowing red from the heat of their birth. But Webb is doing more than just taking pictures. It's using its spectrographs to dissect the light from these protostars. One of the key mysteries of star formation is how the protostar stops growing. As it accretes material, it also has to shed angular momentum. It does this by launching powerful jets of material from its poles. These jets slam into the surrounding cloud, creating beautiful glowing structures called Herbig-Haro objects. Webb's NIRSpec instrument can measure the speed and composition of the material in these jets with incredible detail. This helps scientists understand the physics of how stars regulate their own growth. It can also study the protoplanetary disk around the protostar. It can see the inner regions of the disk where material is being funneled onto the star. It can map the distribution of different molecules like water and carbon monoxide, seeing how they are being heated and processed in this chaotic environment. This is directly connected to the question of planet formation. The conditions in this early stage determine what kind of planets will eventually form. Webb is also studying the very earliest stages of star formation, looking at starless cores. These are the cold, dense clumps of gas that are on the verge of collapsing to form a star. By analyzing the faint infrared light that passes through these cores, Webb can take a chemical inventory of the raw materials just before a star is born. It is looking for the very first signs of chemical complexity. One of Webb's early science programs focused on a protostar called L1520. The image was breathtaking. It showed an hourglass shape of glowing dust, illuminated by the unseen protostar at its neck. Webb's NIRCam instrument could see the structure of the disk around the protostar, seen edge-on as a dark line. This single observation provides a textbook example of the early stages of star formation, giving scientists a huge amount of data to test their computer models. Webb is giving us our first clear look inside the cosmic incubators, revealing the messy, beautiful, and complex process that created our own sun and billions of others. Number 9, the fate of the universe depends on a substance we call nothing. In the late 1990s, astronomers made a discovery that completely upended our understanding of the cosmos and earned a Nobel Prize. They were using Type Ia supernovae to measure the expansion rate of the universe, expecting to see the expansion slowing down due to the gravitational pull of all the matter within it. Instead, they found the exact opposite. The expansion of the universe is accelerating. It's speeding up. Something is pushing space-time apart. This mysterious force or energy was given the name dark energy. It is the most dominant component of the universe, making up about 68% of its total energy density. For dark matter, makes up 27%, and normal matter, everything we can see, is less than 5%. We live in a universe dominated by two things we cannot see and do not understand. The simplest explanation for dark energy is that it is the cosmological constant, a concept Albert Einstein proposed and later called his biggest blunder. It suggests that empty space itself has an intrinsic constant energy. As space expands, more space is created, and so more of this energy appears, pushing the expansion to go even faster. This is the lambda and the standard lambda CDM model of cosmology, but there's a huge problem. When physicists try to calculate how much energy empty space should have based on quantum field theory, the answer they get is absurd. It's about 120 orders of magnitude larger than what we observe. This is the worst prediction in the history of physics. It tells us we are missing something very, very fundamental about how gravity and quantum mechanics work together. Is dark energy really a constant, or is it something else, a dynamic field that changes over time, sometimes called quintessence? If it changes, the fate of the universe could be very different. If the repulsive force of dark energy grows stronger over time, it could lead to a big rip, where everything from galaxies to atoms is torn apart. If it weakens or reverses, the universe could recollapse in a big crunch. Determining the nature of dark energy is one of the most important goals in modern physics. The James Webb Space Telescope can't observe dark energy directly, but it can measure its effects on the history of cosmic expansion with extreme precision. It does this by extending the measurements of Type Ia supernovae to much greater distances. Hubble could observe these supernovae out to a certain distance, covering a certain period of cosmic history. Because Webb is an infrared telescope, it can see supernovae that are even farther away. All the light from these most distant explosions has been so redshifted that it is brightest in the infrared. By finding and measuring these very early supernovae, Webb can map the expansion history of the universe in a new and unexplored epoch. It is looking back to a time when the universe was younger and smaller, and the repulsive force of dark energy was just beginning to overtake the gravitational pull of matter. And did the expansion rate in that era match the predictions of the cosmological constant? Or was it different? Any deviation would be evidence that dark energy is not constant, and that our standard model of cosmology needs to be revised. And Webb is also using other methods like studying the clustering of galaxies at different cosmic epochs. The way galaxies are distributed on large scales is a sensitive probe of the underlying expansion history. By creating a 3D map of galaxies in the distant universe, Webb provides another independent check on the properties of dark energy. These are long-term, painstaking projects. They require observing many different fields of the sky over several years. But the potential payoff is enormous. Webb's data could provide the first clues to solving the mystery of dark energy, a mystery that holds the key to the ultimate fate of our universe. Number 8, cosmic dust is not just annoying, it's a key ingredient. Cosmic dust might sound boring. It's the stuff that gets in the way, that blocks our view of distant stars and galaxies. For a long time, astronomers treated it as a nuisance, but we now know that dust is a critical component of the cosmos. For dust grains, which are tiny particles of silicates and carbon, are the sites where complex molecules form. They are the seeds from which planets grow, and they play a key role in the life cycle of galaxies. The dust absorbs ultraviolet and visible light from young, hot stars and re-radiates it at longer infrared wavelengths. This process cools the gas in galaxies, allowing it to collapse and form new stars. Without dust, galaxy evolution would be very different. So a big question is, where does all this dust come from? We know of two main sources. One is the atmospheres of old dying stars like red giants. As these stars shed their outer layers, the cooler temperatures allow elements like carbon and silicon to condense into solid dust grains. The other major source is supernovae, the explosive deaths of massive stars. The explosions create heavy elements, and in the cooling, expanding remnant, some of this material can form dust. But there's a problem with our accounting. When we look at very distant young galaxies in the early universe, we see that they are incredibly dusty. Some of them are so dusty that they are almost invisible to Hubble. You know, they contain huge amounts of dust that must have formed very quickly within the first billion years of cosmic history. The traditional sources, like old dying stars, simply don't have enough time to produce this much dust. A red giant lives for billions of years. Supernovae happen quickly, but our models of dust formation in their remnants have struggled to explain the sheer quantity of dust we see in the early universe. This is the dust budget crisis. The James Webb Space Telescope is the perfect tool to solve this mystery. As an infrared telescope, Webb is not hindered by dust, it thrives on it. It can see the infrared glow from the dust itself, allowing it to map its distribution and measure its temperature and quantity even in the most distant galaxies. More importantly, Webb is directly observing the sites of dust production. It is studying nearby supernova remnants like Cassiopeia A and the Crab Nebula with its MIRI instrument. MIRI can create chemical maps of these remnants, showing exactly where different types of dust like silicates are forming and how much is being created. It can see if the dust is surviving the turbulent environment of the remnant, or if it's being destroyed by shockwaves. Early Webb observations of a supernova remnant called SN 1987A have already provided crucial new data. Webb was able to see newly formed dust in the very center of the expanding ejecta, confirming that supernovae are indeed efficient dust factories. Webb is also looking at those extremely dusty galaxies in the early universe. By analyzing their infrared light, it can determine not just how much dust they contain, an amount that seems to be far larger than previously thought, but also what kind of dust it is. This can provide clues about its origin. Is it the type of dust expected from supernovae? Or is there some other unknown mechanism for producing dust quickly in the early cosmos? Perhaps dust grains can grow much faster than we thought in the dense interstellar medium of young galaxies. The dust budget crisis is a fundamental problem. It touches on star formation, galaxy evolution, and the chemical enrichment of the universe. Webb's ability to see both the dust and its sources with unprecedented clarity is providing the data needed to balance the books. Number 7, rogue planets may outnumber stars. Our model of a solar system is a star with planets in stable orbits, but the universe is a chaotic place, especially in its youth. Young star clusters are crowded environments. The gravitational interactions between newborn planets and other stars can be violent. These interactions can fling planets out of their home systems, sending them wandering alone through the vast dark space between stars. These are rogue planets, or free floating planets. For a long time, they were purely theoretical. Finding them is exceptionally difficult. They don't have a parent star to illuminate them, so they are incredibly faint and cold. The only way we could find them before was through a technique called gravitational microlensing. If a rogue planet happens to pass almost directly in front of a distant star, its gravity will briefly bend and magnify the star's light, causing a characteristic brightening. By monitoring millions of stars, surveys have found a handful of these events, suggesting that rogue planets exist. But this method is hit or miss and doesn't tell us much about the planets themselves. Some theories predict that these lone worlds could be incredibly common. There might be as many or even many more rogue planets in our galaxy as there are stars. Some simulations suggest there can be 20 rogue planets for every star in the Milky Way. If true, this would mean there are trillions of them wandering through our galaxy. The James Webb Space Telescope offers a new way to find and study these planets directly. While rogue planets are cold and dark, they are not completely cold. Young ones in particular still retain some of the heat from their formation. This means they glow faintly in the infrared, and Webb is the most sensitive infrared telescope ever built. One of Webb's large observing programs is using its NIRCam instrument to survey a dense region of a nearby star-forming region, the Orion Nebula. It is taking deep images of the cluster, looking for faint red objects that are not gravitationally bound to any star. The key is to find objects that are too small to be stars or even brown dwarfs, the failed stars that are not massive enough to ignite nuclear fusion. They are looking for objects with the mass of Jupiter or even smaller. This survey will give us the first real statistics on the number of rogue planets in a young star cluster, telling us how efficient the planet ejection process is. In 2023, an analysis of Webb's early observations of the Orion Nebula revealed dozens of candidate rogue planets, some with masses as small as Jupiter's. What was particularly surprising was that many of them were found in pairs, orbiting each other far from any star. The existence of these binary planets is hard to explain with the ejection theory. It is unlikely that two planets would be ejected together and remain bound. This discovery hints that perhaps these objects formed in a different way, more like tiny stars, collapsing directly from small clouds of gas in a process that falls below the threshold to make a star. Webb is not just finding them, it can also start to characterize them. If a rogue planet is bright enough, Webb can use its spectrographs to try and analyze its faint thermal glow. This could potentially tell us about its atmospheric composition, revealing if it has clouds or molecules like methane and water. The study of rogue planets is a brand new field of astronomy. They represent a huge, unseen population of planetary bodies. Understanding how many there are and how they formed is crucial for a complete theory of planet formation. Webb is opening the door to this hidden part of our galaxy. Number 6, brown dwarfs blur the line between planet and star. There is a gap in our cosmic catalog. On one side, we have stars, massive balls of gas that are hot and dense enough in their cores to fuse hydrogen into helium. On the other side, we have planets like Jupiter, which are much smaller and do not have nuclear fusion. But what lies in between? The answer is brown dwarfs. These objects are often called failed stars. They are more massive than planets, but not massive enough to sustain hydrogen fusion. The dividing line is thought to be around 13 times the mass of Jupiter. Above this mass, an object is hot enough to fuse deuterium, a heavy isotope of hydrogen, for a short time. The upper limit for a brown dwarf is around 80 Jupiter masses. Above that, you have a true star. Brown dwarfs are fascinating because they challenge our simple definitions. They form like stars collapsing from clouds of gas, but they have atmospheres that are cool enough to have weather and clouds like planets. As they age, they just cool down and fade away, becoming harder and harder to detect. because they are not very luminous and emit most of their light in the infrared. They were very difficult to study before Webb. We've found hundreds of them, but getting detailed information has been tough. We want to know what their atmospheres are made of, how their clouds work, and where the precise boundary lies between a giant planet and a small brown dwarf. The James Webb Space Telescope is a perfect machine for studying brown dwarfs. Its infrared sensitivity allows it to see even the coldest and oldest ones. Its spectrographs can dissect their faint light with incredible precision. Webb is observing a wide range of brown dwarfs. For some of the warmer ones, it is mapping their weather. By observing a brown dwarf as it rotates, Webb can detect changes in its brightness. These changes are caused by cloud patterns moving in and out of view. By taking spectra at different points in its rotation, scientists can create a 2D map of the brown dwarf's cloud composition. The clouds are not made of water, like on Earth. They are thought to be made of exotic materials like silicates, rock, iron, and salts, which condense out of the atmosphere at these high temperatures. Webb has already studied a nearby brown dwarf called VHS 1256b. Its observations revealed an atmosphere swirling with silicate clouds, essentially sand clouds, along with clear detections of water, methane, and carbon monoxide. The data was so detailed that it showed the atmosphere was extremely turbulent, with material constantly being dredged up from hotter depths and sinking back down. This is giving us an unprecedented look at alien meteorology. Webb is also tackling the planet-star boundary question. It is looking at some of the lowest mass brown dwarfs and the highest mass exoplanets to compare them directly. Or how do their atmospheric chemistries differ? Is there a smooth transition, or is there a clear dividing line? By building up a library of high-quality spectra for these objects, Webb will help us refine our theories of how stars and planets form. This research is not just about these strange in-between objects. Understanding the atmospheres of brown dwarfs, which are simpler systems without a bright host star to complicate things, helps us interpret the data we get from the atmospheres of giant exoplanets. Brown dwarfs are a stepping stone to understanding the worlds orbiting other stars. Number 5, the first galaxies were not like the ones we see today. Our picture of a galaxy is something like the Milky Way or Andromeda, a majestic, well-ordered spiral disk with a central bulge. But it took billions of years for galaxies to evolve into these mature forms. What did the very first galaxies look like? Our models, based on the theory of cold dark matter, predicted that the first galaxies would be small, clumpy, and irregular. They would be the building blocks, the dwarf galaxies, that would then merge over and over again to build up the large galaxies we see today. It should be a gradual bottom-up process. The Hubble Space Telescope gave us our first glimpses into this early era. Its deep field images revealed some of these distant young galaxies. They did look smaller and more irregular than modern galaxies, which seemed to support the model. But Hubble, being primarily a visible light telescope, could only see the brightest of these galaxies, the ones with lots of hot young blue stars. It was getting a biased view, potentially missing a huge population of smaller, fainter, or dustier galaxies. The James Webb Space Telescope was designed to overcome this. It is a galaxy-finding machine for the early universe, and its large mirror and infrared detectors can see galaxies that are 10 to 100 times fainter than what Hubble could detect. And its early results have been both spectacular and puzzling. Webb has found many more galaxies in the early universe than expected. It has found galaxies that are surprisingly bright and well-developed at very early times, just 300 to 500 million years after the Big Bang. Some of these galaxies appear to be surprisingly massive. This challenges the idea of a slow, gradual buildup. It seems that galaxy formation kicked into high gear much earlier and more efficiently than our models predicted. It's like arriving at a party an hour after it started and finding everyone already there and the place fully decorated. Another surprise is the shape of these early galaxies. While many are clumpy and irregular as expected, Webb has also found a surprising number of galaxies that appear to have disk-like structures much earlier than predicted. The ordered rotating disks of spiral galaxies are thought to take a long time to form and settle down. Seeing them so early is a puzzle. It might mean that the early dark matter halos were more stable than we thought, or that the gas within them could cool and settle into a disk much more quickly. Webb is not just taking pictures. Its near-spec instrument is a game changer. It can take spectra of hundreds of galaxies at once in a single deep field observation. This tells us their exact distance, their redshift, and their chemical composition. With Hubble, getting a spectrum for a faint, distant galaxy was a long, difficult process, taking many hours of telescope time for a single object. The Webb does it in bulk. This is allowing astronomers to build the first large, unbiased census of galaxies in the cosmic dawn. The initial spectroscopic results have confirmed that these galaxies are indeed as distant as they appear, and their light shows the chemical signatures of the first generations of stars. They are rich in hydrogen and helium, but have lower amounts of heavy elements compared to modern galaxies. This is exactly what we expect for young galaxies that have not had much time for stellar evolution to enrich them. The data from Webb is forcing theorists to go back to their simulations. Perhaps star formation was much more efficient in the early universe. Perhaps the first stars were even more massive than we thought, producing more light. Or maybe the way gas flows into and out of early galaxies is different from our models. Webb is providing a flood of high-quality data from an era of cosmic history we could barely see before. It is showing us that the birth of galaxies was a more rapid and dramatic affair than we ever imagined. Number 4, we don't know how the interstellar medium is recycled. The space between the stars is not empty. It's filled with the interstellar medium, or ISM. This is a mix of very dilute gas, mostly hydrogen and helium, dust, and cosmic rays. It's the raw material from which new stars are born, and it's also the repository for material ejected by dying stars. The ISM is in a constant cycle. Gravity pulls gas and dust together to form stars. Stars process this material through nuclear fusion, creating heavier elements. At the end of their lives, stars return this enriched material to the ISM, either gently through stellar winds or violently through supernova explosions. This newly enriched gas then cools and forms the next generation of stars. This is the cosmic engine of galaxy evolution. Understanding the cycle is fundamental to understanding how galaxies like our own live and breathe. But there are many details we don't understand. How exactly does the energy from supernovae and young stars stir up and heat the ISM? How does the hot, enriched gas from these explosions mix with the surrounding cold gas? And how does the gas cool down again to form new stars? These processes happen on many different scales, from individual supernova remnants to giant superbubbles blown by clusters of massive stars. And much of it happens in dusty regions hidden from optical telescopes. The James Webb Space Telescope is giving us a new window into this complex cycle. Its infrared instruments can peer through the dust to see the processes at work. It can also detect the specific spectral lines from molecules and ions that trace the different phases of the ISM, from cold molecular gas to warm ionized gas. One of Webb's key targets is the Large Magellanic Cloud, a small satellite galaxy of the Milky Way. It's close enough that we can resolve individual stars and nebulae, but it's also a very active galaxy with lots of star formation. It's a perfect laboratory for studying the ISM. Webb is mapping regions of the LMC in stunning detail. For example, it has taken images of the Tarantula Nebula, one of the most extreme star-forming regions in our local galactic neighborhood. The images reveal thousands of never-before-seen young stars and intricate structures of gas and dust being carved out by the intense radiation and stellar winds from the massive star cluster at the nebula's heart. Webb's spectrographs are also crucial. MIRI and NIRSPEC can map the distribution and motion of different types of gas. They can see the shock waves from supernovae propagating through the ISM. They can measure the chemical composition of the gas in different regions, seeing exactly how the heavy elements produced by stars are being mixed back into the interstellar soup. A particular focus is on a type of large molecule called polycyclic aromatic hydrocarbons, or PAHs. These carbon-based molecules are found throughout the ISM and are very bright in the infrared. They are a key tracer of the physical conditions in the ISM and play an important role in its heating and cooling. Webb spectra can identify specific PAHs and see how they are formed and destroyed in the harsh environment near young stars. By observing these processes in detail in our galactic backyard, we can build better models to understand what's happening in distant, unresolved galaxies. The ISM recycling process determines a galaxy's star formation rate and its chemical evolution. Webb is providing the detailed local observations needed to understand this grand cosmic cycle. Number 3, stellar death is the engine of cosmic creation. A star's death is not an end. It is a spectacular act of cosmic recycling. The elements that make up our planet and our bodies, the carbon, oxygen, iron, were all forged in the hearts of stars and scattered into space when those stars died. Low-mass stars like our sun die relatively gently. They swell up into red giants and then puff off their outer layers to form a beautiful, glowing structure called a planetary nebula, leaving behind a dense core called a white dwarf. Massive stars, those more than about 8 times the mass of the sun, die in a much more dramatic fashion. They end their lives in a cataclysmic supernova explosion, one of the most energetic events in the universe. For a few weeks, a single supernova can outshine its entire host galaxy. These explosions are responsible for creating and distributing many of the heavy elements. But there are still many unanswered questions about how stars die. For planetary nebulae, we don't fully understand how they get their often complex and beautiful shapes. The dying star is a simple sphere, but the nebulae can be bipolar, with intricate rings and jets. What shapes them? Is it the influence of a binary companion star? For supernovae, the details of the explosion mechanism are still a matter of intense debate among theorists. We also don't know for sure which types of massive stars lead to which types of supernovae. And as mentioned before, a key question is how much dust is created in the aftermath. The James Webb Space Telescope is observing both types of stellar death with its powerful infrared eyes. For planetary nebulae, Webb's images have revealed breathtaking new levels of detail. Its famous image of the Southern Ring Nebula showed intricate shells of gas and dust ejected by the dying star. But the real surprise was that the central star was revealed to be a close binary pair. This provides strong evidence that a companion star plays a key role in shaping the nebula. Webb's spectrographs can also dissect the light from these nebulae, creating maps of their chemical composition and temperature, helping us understand the complex chemistry that happens as the dying star's material is reprocessed. For supernovae, Webb is studying their remnants. These are the expanding clouds of gas and dust left over from the explosion. Because Webb can see in the infrared, it can detect the warm glow of the dust that forms in these remnants. It can also detect the spectral lines from the newly synthesized heavy elements. It is making detailed maps of remnants like Cassiopeia A, the result of a supernova that exploded around 340 years ago. These maps show us where elements like argon, silicon, and sulfur are located within the ejecta. This provides a 3D picture of the stellar explosion itself, giving us clues about the asymmetries in the original blast. This data is a direct test for the complex computer models of supernova explosions. By studying these nearby remnants, the crime scenes of stellar death, Webb is helping us understand one of the most important processes in the cosmos. It's a process that is both destructive and creative, tearing stars apart, but also seeding the universe with the ingredients for the next generation of stars, planets, and life. Number 2, the Hubble Tension might mean we need new physics. The Hubble tension is the conflict between the two leading measurements of the universe's expansion rate. The local measurement using stars and supernovae gives a value of about 73. The early universe measurement, based on the cosmic microwave background, gives a value of about 67. The fact that these two numbers derived from completely different methods and different cosmic eras do not agree is a huge red flag for cosmologists. It suggests that our standard model of the universe, the lambda CDM model, might be wrong or at least incomplete. The lambda CDM model has been incredibly successful. It explains the CMB, the large-scale structure of galaxies, and the abundance of light elements. It's based on just 6 parameters. The fact that we can describe the entire universe with a simple model is a remarkable achievement. But the Hubble tension is a crack in this beautiful edifice. There are 3 main possibilities. The first is that there is some unknown systematic error in the local measurement. The cosmic distance ladder is a complex process with many steps, and there could be a mistake somewhere that we haven't found yet. The second possibility is an error in the early universe measurement. This is considered less likely as the physics of the CMB is very well understood and the Planck satellite's measurements are extremely precise. The third and most exciting possibility is that both measurements are correct and our model is wrong. There might be some new physics that we don't know about. This is where Webb's role becomes so critical. Webb's primary job in this area is to attack the first possibility. It is designed to reduce or eliminate the known systematic errors in the local measurement. By using its sharp infrared vision to re-observe the Cepheid variable stars used to calibrate the distance ladder, Webb can get cleaner measurements, less affected by dust and stellar crowding than Hubble could. The SH0ES supernovae H0 for the equation of state of dark energy team, which made the leading local measurement with Hubble, is now using Webb to refine their work. The goal is to get the uncertainty on the local measurement down to just 1%. If Webb's more precise measurement confirms the 73 value, it will make the tension with the 67 value from the CMB even more statistically significant. It would essentially rule out measurement error as the explanation, forcing us to confront the third possibility, new physics. What could this new physics be? There are several ideas. One is early dark energy. This theory suggests that in the very early universe there was an extra form of dark energy that was present for a short time and then decayed away. This would have changed the expansion rate in the early universe, which would in turn alter our interpretation of the CMB data, potentially bringing the 67 value up to match the 73 value. Another idea involves new types of particles like a new kind of neutrino, sometimes called a sterile neutrino. These particles would add to the dark radiation in the early universe, again changing its expansion dynamics. Or perhaps our understanding of dark matter is too simple. Maybe dark matter has some weak interaction with other particles that we haven't accounted for. Webb itself can't prove any of these new theories directly, but by providing a definitive measurement of the local Hubble constant, it can close the door on mundane explanations and tell the physics community whether they need to seriously look for a new model of the cosmos. It is putting the standard model of cosmology to its most stringent test yet. Number 1, are we alone? This is perhaps the most profound question we can ask. Is there life elsewhere in the universe? For all of human history, this has been a question for philosophers and science fiction writers. Now, for the first time, we have the technology to begin answering it scientifically. The James Webb Space Telescope is at the forefront of this search. Webb cannot detect life directly. Can't see alien cities or forests, but what it can do is search for biosignatures. These are chemical clues in a planet's atmosphere that could hint at the presence of biological processes. On Earth, our atmosphere is filled with oxygen, but oxygen is a highly reactive gas. It shouldn't be there in such large quantities. It is constantly replenished by life through photosynthesis. The combination of oxygen and methane in our atmosphere is a particularly strong biosignature because these two gases would normally destroy each other. Seeing them both together implies there is a massive source for each, which on Earth is life. Ed Webb's primary method for searching for these clues is transit spectroscopy, studying the starlight that filters through an exoplanet's atmosphere. It is looking for the spectral fingerprints of key molecules like oxygen, methane, water vapor, and carbon dioxide. The goal is to find a planet, likely a rocky Earth-sized world in the habitable zone of its star, that has an atmospheric composition that is out of equilibrium, one that cannot be explained by geology or photochemistry alone. The TRAPPIST-1 system is a prime target for this search, as are other nearby systems with potentially habitable planets. But this is an incredibly challenging task. The signals are minuscule, and we have to be extremely careful about false positives. For example, it might be possible to produce oxygen through non-biological processes like water vapor in the upper atmosphere being broken apart by starlight. We need to understand the planet's context, its star, and its geology before we can claim a detection. Webb is taking the first crucial steps. It is building a foundational library of exoplanet atmospheres. By studying a wide variety of worlds, from gas giants to super-Earths, we are learning what normal looks like for planetary atmospheres. This will help us recognize something truly anomalous if we see it. The detection of methane and carbon dioxide on the Hycean world K2-18b and the tentative hint of dimethyl sulfide is an early and exciting example of this process. It has sparked a huge amount of follow-up research and debate. It shows that Webb can detect these molecules. The question now is whether it can find them in the right combination on the right kind of planet. Even if Webb doesn't find a definitive biosignature, its work is revolutionary. It will tell us whether potentially habitable planets have atmospheres at all. It will tell us if they have water. It will characterize the environments that could one day be the targets for future telescopes designed specifically to find and image Earth-like worlds. This Webb is not the final answer in the search for life. It is the beginning. It is the first tool powerful enough to move the question from the realm of speculation into the world of observational data. It is taking our first real scientific steps toward answering that ultimate question, are we alone in the universe?